All right, so we've looked at logarithmic equations, and we want to do exponential equations. That's what we want to work on. I think exponential equations can be a little harder. I guess it depends on your perspective and what you're comfortable with. Important fact before we get into working these, remember, we've talked about this in the past. If you have a positive number, a, then a to any power, x, is always going to be positive. So always remember a to a power is positive when a is a positive number. So here we go. Let's start solving some exponential equations. So exercises. Determine the exact solution to the equation. So when I say exact solution, I mean if you get some expression that's weird, I don't know, let's say it has a natural log in it or an e in it or something like that. Don't approximate it in your calculator, just give the exact expression. Or if I had like the square root of 55, don't approximate the square root of 55 in your calculator, just write the square root of 55 because that doesn't reduce nicely. So I don't want any rounded off approximations in the calculator. I want exact numbers. Okay, so here's number one. So the good thing about exponential equations, you don't have to worry about the argument, the restrictions on the domain. The restrictions on the domain, you don't have to worry about those, like with the logs. Okay, number one. Let's say I have 3 raised to the x plus 5 power, set equal to 81. So if I wanted to solve that, so this is an exponential equation because you have exponential expressions set equal to each other. So here we have a exponential base 3. So we want to say, okay, can you possibly write 81 here on the right side in terms of exponential base 3? And the answer is yes. So I'm going to copy down the left side as it is, 3 raised to the x plus 5. And on the right-hand side, I'm saying, okay, can I rewrite 81 as 3 to some power? Yeah, 3 to the 4th power, right? 3 to the 4th power is 81. So now that our exponential bases match, right, we have a base 3 here and a base 3 here, what we can do is match up the exponents. X plus 5 and set it equal to 4. So I'm going to set x plus 5 equal to 4. And from there you just subtract a 5 from each side, and you get x is -1. That's it. You don't have to worry about any restrictions on the domain here, like with the logarithmic functions. You don't have to check anything. You just get your answer. Okay, number 2. Let's say I have 9 x minus 4 is my exponent equals 3 x plus 7 is my exponent. And my question is, okay, I have these two exponential bases, base 9 and base 3. Can you find a common base for them? They both can be written in terms of base 3, right? 9 can be written as 3 squared. So I'm going to rewrite 9 as 3 to the 2nd power. That's another name for 9. I'm going to keep this argument here of x minus 4. And then that's equal to 3 to the x plus 7. Now, I'm going to use my properties of exponents. I'm going to take 2 and multiply it by x minus 4. So I'm going to write this as 3. And my exponent here is going to become 2 times x minus 4 equals 3 to the x plus 7. So now we can take since our bases match, we both have base 3 and base 3 on each side, we can take our exponents and set them equal. So we have, 2 parentheses x minus 4 equals x plus 7. So if I wanted to solve this equation, I would, first of all, distribute on the left side. I'd distribute by 2. 2 times x is 2x. 2 times negative 4 is negative 8. And on the right side, I keep x plus 7. I get all the x's on one side. Let's get the x's on the left side, so I subtract x from both sides. 2x minus x is x. And then let's say we want to get all the numbers on the right, so I'd add 8. And I get x equals 7 plus 8 is 15. So my solution here would be 15. You don't have to check anything here. Number 3. Let's say I had 4 raised to the x power plus 1 equals negative 15. I'm sorry, negative 17. No, I was right, negative 15, I was right. If I wanted to solve this, what I would do, I would try to get the 4 to the x by itself. I want to get this exponential part by itself, right? It's connected to something else, a plus 1. So to get rid of the plus 1, I would subtract a 1 from each side. And that would give me 4 to the x equals negative 15 minus 1 is minus 16. Now you might be tempted to try to write negative 16 in terms of 4 to some power, but you can't. This is a negative number right here, right? This is a negative number. Remember that 4 to a power is always positive, so this is not going to have a solution. So note that 4 to a power must always be greater than 0, must always be positive, can never be negative. So because this cannot happen, we're going to have no solution to this equation. Yeah. So 4 to the x power always has to be positive. When you take a positive number to a power, it's always positive. That's our fact up top here. So no solution. Okay, let's take a number 4 here. Let's say we have 1 over 25, and 25 in the bottom is raised to the x plus 2 power. And then that's equal to 125 to the x minus 3 power. So I'm going to focus on this base 125 and this base 25. I'm going to ask, do they have a common exponential base? Yes, they both can be written in terms of 5 to a power. So I'm going to write 1 over, so I'm going to write 25 as 5 to the 3rd power. No, 5 to the 2nd power, right? 25 is 5 squared. And that's going to be raised to the x plus 2 down on bottom. And then the other one, the 125, can be written as 5 to the 3rd power. Right, 125 is 5 to the 3rd power. That has an exponent of x minus 3. So I'm going to rewrite the left side as 1 over 5. And what we're going to do, we're going to take 2 here. And that's going to be times x plus 2. Using properties of exponents, equals, and on the right side 5, and then we're going to have 3 times x minus 3. Now notice on the left side that we have this weird fraction, right? We have this 5 to the 2 times x plus 2. It's on bottom. So to take that up top, that's what we want to do. We're going to take that up top. We're going to write it as 5. And we're going to change the exponent to a negative. It's going to become negative 2 times x plus 2. So when you take it up top, it becomes a negative. And that's equal to 5 to the 3 times x minus 3. So thankfully, our bases match, so we can get rid of those and just set the exponents equal. So negative 2 times x plus 2 equals 3 times x minus 3. And we'll distribute on the left side the negative 2. We'll get negative 2x minus 4. And on the right side, we'll distribute the 3. We'll get 3 times x minus 9. So if we wanted to solve for x, we would add 2x to both sides. And we'll get negative 4 equals 5x minus 9. And we'll add a 9 to both sides, looks like. So on the left side, negative 4 plus 9 is 5 equals 5x. And then just divide both sides by 5. And you get, the 5's cancel on the right, you get x equals 1. So 1 is the solution here. That was a number 4. Okay, let's do a number 5. We have 2 multiplied by 6 to the x minus 3 equals 7. Now, one mistake that students sometimes try to do, they try to multiply this 2 times the 6, and they'll say 12 to the x. That's wrong. You can't do that. It doesn't allow you to do that. That is wrong. So the goal here is that you want to get the 6 to the x by itself. So you want to get this red dude by itself, 6 to the x. So to get rid of, first of all, the goal is going to be get rid of the minus 3, so I'm going to have to add a 3 to both sides. So I'm going to have 2 times, some people write it this way, 2 times 6 to the x. Then we have equals, so here the negative 3 and the positive 3 cancel on the left, and on the right we have 7 plus 3 is 10. Okay, and then you want to get rid of this multiplication by 2 here. So we're going to divide both sides by this 2. The 2's cancel on the left. If we're going to get 6 to the x equals 10 divided by 2 is 5. Now it turns out if you were to try to find a common base here between 6 and 5, you can't find a common base. There is no common exponential base. So what do you do in those cases? What do you do when there's no common exponential base? What you can do is, you see here you have an exponential base 6. So what we're going to do, we're going to take a log base 6 of both sides. So I'm going to write down, I'm going to take the log base 6 of both sides. So we're going to take a log base 6 of the left side, 6 to the x, and then the right side, which is log base 6 of 5. Now the reason why we're taking the log base 6 of both sides is so we can cancel out the log base 6 with the exponential base 6. Remember, that's one of our inverse properties of logarithms. So when you can't find a common exponential base, just take the log base, in this case 6. So what will happen is the x will drop down as the log base 6 cancels with exponential base 6, and you get log base 6 of 5. And that's your answer. You really can't reduce that in a nice way. This is probably going to be a really strange decimal. If you type that in your calculator, you'll get a strange decimal. And we don't want to write in that decimal because that decimal would be rounding something off. It doesn't give you an exact answer. We want the exact answer. That's what the instructions were, to give the exact answer. Okay, let's do another one. Let's do number 6. We have 7 times 8 to the 2x minus 1 plus 9 equals 58. And the goal is to solve for x. So to get x by itself, we'll first have to get the exponential part by itself. So this exponential expression here we want to get by itself. So first we're going to get rid of the plus 9. We're going to subtract 9. that'll give us 7 times 8 to the 2x minus 1 on the left side, and on the right side we'll have 58 minus 9 is 49. Okay, then we have to get rid of this multiplication by 7, so we're going to divide both sides by 7. The 7s will cancel on the left, and you'll have 8 to the 2x minus 1 equals 49 divided by 7 is 7. Now my question to you is, do 8 and 7 have a common exponential base? Can you both write those in terms of something to a power? And the answer is no. No. There's nothing in common between 8 and 7. So what we're going to do, we're going to get rid of this exponential base 8 by taking the log base 8 of both sides. So I'm going to take log base 8 of the left side, 8 to the 2x minus 1. I'm going to do it to the right side. I'll take the log base 8 of 7. So using our logarithmic inverse properties, we're going to take log base 8 and cancel it with exponential base 8, and we're going to have 2x minus 1 equals log base 8 of 7. So all I have to do now is to get x by itself, so I'll add 1 to both sides, and I'll have that 2 times x equals log base 8 of 7 plus 1, and the final step is just divide both sides by 2. I get rid of the 2's on the left, and I get that x is log base 8 of 7 plus 1, all divided by 2. And there's my solution. Don't try to approximate this in your calculator, because that's not an exact solution. That would give you a round off error. A little bit of error. It'll be close, but it won't be exact. And that's what we want. We want exact solutions here. Okay. Now let's see if we can do maybe a couple more. Do number 7. Let's say we have 7e to the 7x plus 12 plus 1 equals 31. So what I want to do, I want to solve this for x. So I'm going to have to get this exponential right here by itself, this exponential expression. So first I got to get rid of the plus 1, so I'm going to subtract 1 from each side. I have 6 times e to the 7x plus 12 equals 31 minus 1 is 30. Okay, now we have to get rid of this multiplication by 6 out front, so we're going to divide both sides by 6. Whereas the 6's will cancel, and we'll get the exponential expression e to the 7x plus 12 equals 30 divided by 6 is 5. And then you see, okay, can you write e and 5 in terms of a common exponential base? And the answer is no. E and 5 have no common exponential base. Remember that e is approximately 2.718. It's a very unusual number. So rather than trying to find a common base like we do sometimes, we're going to take the log base e of both sides. So we'll have the log base e of e to the 7x plus 12 on the left, and on the right, the log base e of 5. So log base e cancels with exponential base e on the left, and we get 7x plus 12 equals. Now remember, another name for log base e is the natural log. I'm going to write it as ln of 5. ln of 5, natural log of 5, is the same as log base e. So from there, you want to get the x by itself, so let's subtract 12 from each side. We get 7x equals the natural log of 5 minus 12. And then we just divide both sides by 7 to get the x by itself. Whereas the 7's will cancel on the left, and we get x equals the natural log of 5 minus 12 divided by 7. And there's your solution. Don't try to plug that in a calculator and round it off. We want the exact solution, not a rounded off error solution. So that's exactly it. Okay, I guess we'll do one more. The last one will be a little bit more challenging, and there'll be multiple ways to do the last one. Let's say we have 5 raised to the x minus 8 power equals 6 to the 2x plus 9 power. So notice here that you have 2 exponential bases, 5 and 6, and you cannot come up with a common base for those. 5 and 6 have no common exponential base. So you can't use that trick that we sometimes use where you find a common exponential base. So you can do one of two things. So I'll do method 1. You want to get rid of one of those exponential bases, where method 1 you take log base 5 of each side. So I'm going to do that method. So I'm going to take the log base 5 of both sides. So I take the log base 5 of 5 to the x minus 8, and I take the log base 5 of 6 to the 2x plus 9. And that looks really strange. Let's try it again. 2x plus 9. So if I look at my left side, my log base 5 will cancel with my exponential base 5, and I'll have x minus 8 drops down, equals, now we can take this exponent I'm circling in blue and use one of our properties of logs, one of our expansion properties, where we take that exponent out front. 2x plus 9 is going to come out in front of the log base 5 of 6. So on the left, I'll have x minus 8, and I can distribute the log base 5 of 6 through here. I'm going to multiply it through. I'm going to have 2 times the log base 5 of 6 times x, and then we're going to multiply through at the 9, so we'll have plus 9 log base 5 of 6. So we just distributed that yellow log base 5 of 6 through. Then after you do that, you want to get all your x's on one side. I'm going to get all my x's on the left side. So I'm going to subtract 2 log base 5 6 of x from each side. 2 log base 5 of 6 x from each side. So on the right, these will cancel. On the left, I will have x minus 2 log base 5 6 of times x. And I also have a minus 8, and that's equal to, on the right, 9 log base 5 of 6. So I have all my x's on the left, right? I have an x here and an x here. That means on the right, I want to get all my numbers that are not having x's in them, so I'm going to add this 8 to both sides. That means I have x minus 2 log base 5 of 6 times x on the left, and on the right, 9 log base 5 of 6. Maybe make that yellow. Plus 8. Okay, so we got the x's on the left and the numbers that have no x's on the right. On the left, we're going to take this x in common and factor it out. We're going to take out an x. And we'll have, let's see, 1 minus 2 log base 5 of 6. And on the right, we'll have 9 log base 5 of 6 plus 8. And finally, to complete this, we're going to divide both sides by the green to get the x by itself. So I'm dividing both sides by 1 minus 2 log base 5 of 6, whereas the greens will cancel on the left, and we'll have x equals 9 log base 5 of 6 plus 8 over 1 minus 2 log base 5 of 6. So that's one way to write your solution. Now let me show you another method, method 2. So method 1, we got rid of the exponential base 5 by taking log base 5 of both sides. You can also take the log base 6 of both sides and get rid of the right side's exponential base 6. So that's the second method. Method 2 is another way to do it. So take log base 6 of each side. So if I take the log base 6 of each side, I have, let's see, log base 6 of 5 to the x minus 8 equal to log base 6 of 6 to the 2x plus 9. So in this instance, on the right side, the log base 6 cancels with the exponential base 6, and you'll have a 2x plus 9 that drops down. On the left side, you're going to take your blue circled exponent of x minus 8 and pull it out front using your properties of logarithmic expansions. So you have x minus 8 times log base 6 of 5 on the left. So then you'll distribute the yellow log base 6 of 5 through. So you take log base 6 of 5 multiplied by x, and then minus log base 6 of 5 multiplied by 8. So I'll write this as negative 8 times the log base 6 of 5. And that's all equal to 2x plus 9. I'll get all the x's on the left, so I'll subtract 2x from both sides. Whereas I'll have log base 6 of 5 times x minus 2x minus 8 log base 6 of 5 equals, these cancel, 9, and then get all the numbers on the right that don't have x's in them. So we'll add 8 log base 6 of 5 to each side. And that'll give us on the left log base 6 of 5x minus 2x. And on the right, these cancel. On the right, we'll have a 9 plus 8 log base 6 of 5. And then notice on the left, you have these x's in common, so we can factor out an x. When we factor out an x on the left, you have log base 6 of 5 minus 2. Yeah, that's equal to 9 plus 8 log base 6 of 5. And then to eliminate the blue on the left, you divide both sides by blue log base 6 of 5 minus 2. So do it on the left, do it on the right. On the left, blues cancel, and you get x is 9 plus 8 log base 6 of 5 over log base 6 of 5 minus 2. That's another way to do it, and it turns out these are the same solutions. They look quite different, right? They do look different.